All right, well, I've got 5:03, so let's get started. I want to start first by welcoming everybody to our spring faculty research reception. My name is John Conroy. I'm the chair of the Alumni Faculty Committee for the Civil and Environmental Engineering Alumni Association. I want to thank everyone for taking time in their day to join us tonight. We have a good turnout. I think right now we've got about 50 people already on the call and over 140 people have registered for tonight's program. So I'll just give you a brief overview of tonight's program, and it's as follows. First, we'll hear from our new department head, Dr. Anna Barros, and then that will be followed by Professor John Popovics, and he'll be presenting on the Kavita and Lalit Bahl Smart Bridge. And following that, Professor Popovics will be joined by other CE faculty attendees to help answer any questions you may have about his presentation. We plan to wrap the program up around 6 o'clock Central Time tonight. So that's our agenda for tonight. And so next up, we're going to now hear from our new department head, Dr. Anna Barros. So just a little bit of background about Dr. Barros. She is the Donald Bigger Willard Chair of Engineering and is the first woman in history to lead the department as head of the Civil and Environmental Engineering Department at Illinois. Before joining CEE in February, Dr. Barros was the Edmund T. Pratt Jr. School Distinguished Professor of Civil and Environmental Engineering at Duke University. Dr. Barros's research interests are in hydrology, hydrometeorology, and environmental physics, with a focus on water cycle processes in the coupled land, atmosphere, biosphere system, and particularly in the regions of complex terrain. She is a member of the National Academy of Engineering, a fellow of the American Society of Civil Engineers, a member of the American Meteorological Society, the American Association for the Advancement of Science, and the American Geophysical Union. So with that, I'll turn the program now over to Dr. Barros.
Well, I am so happy I was able to make it. Good afternoon, everyone. It seems that Zoom is not working very well on this side of the country in the East Coast. So I wonder actually if anyone had also the same difficulties I did. So I was able to finally get in, and I am very happy to be here. I started on the 1st of February, so it's not been even 2 months, but I had the privilege of meeting several of you in meetings with students or in other occasions. And so I'm looking forward to meeting you in person, hopefully not in a too far distant future. This is the project that you're going to hear about this afternoon is really important to CEE. And as you know, you have heard a lot about it for the last 5 years, I suspect. And you'll probably continue to hear about it for a few years. We're investing in a very important piece of infrastructure, but also, you know, what's interesting about this building is that, as you can see, you look at the faculty and they are coming from all different areas in the department. So this bridge actually is a way of bringing people together that is more than just, a building. And so we're excited about this. We're excited about what will happen in the next few years and our plans for the next decade. And so I am looking forward to meeting with you all in April and speaking to you about our plans, our aspirations, and the state of the department and so on. And without much more to say at this point, I'm going to pass the baton to John, who's our associate head for undergraduate studies in space and many other hats. So one of the impressive characteristics, I think, of CE, which you probably already know, is the amazing people in this department and all kinds of things that people do and how hello, and so people is really our greatest strength. And so, John, take it away. Thank you very much, everyone.
Well, yeah, thanks very much, Anna, and welcome. It's nice to see so many faces. I recognize a lot of names from recent times and from long ago, and some friendly faces. So it's great to see that. As Anna mentioned, I'm now the associate head and director of undergraduate studies, and as part of that role, I'm responsible for space issues, and that includes monitoring what's going on with our facilities, old and new. So it's really a privilege for me to kind of share with you what's going on with our new building, and I'll focus on our impressive bridge, but I will also spend some time on that. And I'll do it through PowerPoint, so I'll share that now. All right, and hopefully this will work. Now earlier I tried to get rid of, this thing. I don't know if you see you see only one screen or you see the presenter view, but I can't get rid of presenter view for some reason. So if you see that, I apologize. So normally,
John,
yeah.
if you look up there, do you see in the top of bar, it says display settings? Right across the top of your screen.
Oh, yeah. Mm-hmm.
Say switch, right there, you can say swap presenter view and slideshow.
Ah, there you go. Thank you, Bill.
Sure.
I tried to do that with the other menu and it wouldn't let me do it. So Bill Spencer saves the day yet again. Thanks, Bill.
Exactly.
Normally this would be a nice event. It would be held up in Chicago and we'd see you face to face, and it's called the CE Faculty Research Reception, and a faculty member talks about that research. But today it's a little different. It's virtual, and we'd like to take the opportunity not to talk about our specific research, but about an opportunity that was presented to us. And that opportunity was to kind of, as faculty, come together and think of how can we add on value to this new building for our students? What can we do about that? And today's presentation will talk about that. So it's not a normal research presentation, but rather talking about collectively what some of the faculty have come together to do to try and achieve that. So I'll talk about mainly the Kavita and Lalit Bahl Smart Bridge, which you see right here. You see that it's a pretty impressive structure. It's a very stout steel frame structure, but it also has this kind of suspended feature, as you see here, which kind of harkens to like the great civil engineering landmark. So I think it's a really kind of impressive structure, and I think the design really is appropriate for what we do here. So I'll be talking about this. A couple things I want to point out before we go on is you see this little thing up here. That's a weather station. I'll talk more about that. And in this photo, we're looking east, right? So this is the new civil and environmental engineering building. I'll talk about that. Some things to note about that. This is the Alumni Center up here. These are faculty offices. This is a collaboration space, the Liebman collaboration space. You see these kind of blue tiles. They kind of evoke water because this building was the Hydrosystems Lab before, and you see that, and there'll be some kind of nice features that aren't up yet. Newmark building is on the right here, so the bridge connects the third floor of the new civil and environmental engineering building to the third floor of Newmark. And again, we're looking east. So that is the computer science building, that's NCSA, and that's Urbana and beyond. Okay, first I'd like to take this opportunity to talk a little bit about the building, because I realize that many of you, including some faculty, would like to have an update about it. So let's talk about that first. And this is what used to be there when it was being constructed. This is the old constant head water tank. Marcelo Garcia loves that thing. It's probably a sad day when that came down. But I like this photo because it kind of shows what we did with the old building. So there used to be the Hydrosystems Lab, which was composed of faculty offices and classrooms and so on. And then it butted up against this building here, which is the Vente Chow Hydrosystems High Bay Lab. Now, that building that it butts up against is still there. We just excavated from the street. You see here, we excavated to there, got rid of everything and put in a new building. This old constant head water tank is replaced with a new pump and sump system that does the job, but without constant, big constant tank. So that's the old. This is a rendering of the new. So here again, you see this is all new building, starting butting up against the Vente Chow Hydrosystems Lab, which is still there and does everything as before. But it comes all the way south to this sidewalk here, and it has these features that kind of evoke the idea of water and waves. However, this building is more than just water and waves. It's all of civil engineering will be represented here. And here's another perspective now looking west at the Kavita and Lalit Bahl Bridge. Okay, a little bit about this building. So this building offers a lot. So we have classroom space, faculty and office, staff offices, lots of graduate student space, teaching and research labs, these kind of really nice collaboration spaces, conference spaces, and display spaces. And here I just show the second floor just to give you an idea, flavor of the whole building. And what you'll see is that we have these nice large classrooms. This is the Wilbur Millhouse family classroom. We have these large graduate student spaces. Here are some examples of faculty office. This is a distinguished faculty office. That's the Newmark faculty office. And we have conference rooms, and we have these really nice, well-lit, very cool collaboration spaces. And this one is the Judith and John Liebman Gallery collaboration space, right? So just to give you a flavor that, you know, this building offers a lot. And then the High Bay, the Vente Chow Hydrosystems High Bay is right here. Okay, so just to give you an idea of kind of the neat, innovative teaching spaces that will be included in the new building, I give you two examples. And I want to thank Professor Jeremy Guest for helping me out with this material. So what we have here is the new Vern Snoyink Water Chemistry Laboratory. It's a large teaching space on the ground floor, and it's meant to be a teaching lab, right? So it's not a conventional classroom. And so we have these kind of workstations, as you see on the left, and they're mobile that you move here. And also on the wall, we have laboratory equipment, right? So this will provide new, unparalleled opportunities for hand-on experiences for water classes for both our undergraduate and graduate students, right? Now, another very interesting lab, again, courtesy of Jeremy Guest, is the Resource Recovery Lab. And this is in the basement. And this is a lab that will use real-life wastewater from our building to kind of help students understand source separations and streams in the wastewater systems, right? So we'll use actual wastewater from our building and be recovered here and used in graduate and undergraduate labs. So really unique kind of resources that have been built into this building, right? And then Jeremy Guest is online. So at the end of this, if you have any questions about any of this or if anything else, we'd be glad to kind of address those. Okay, now, I thought maybe some of you would like to see where we are right now. So yesterday I went to the building, still under construction. It's due to be finished in May, June. Here's some photos of the interiors for your interest. On the left is the interior of the bridge looking to the north. So we're looking at the new building. You see it's quite a wide space. It's a really stout, nice structure. And here you see the feature of the suspension cable here. So it's going to be a really nice space, and you'll see that it's much more than just a bridge between two buildings. Here is on the right is a photo of that collaboration space. So you can see it's on the north end of the bridge, comes out here, spills out to here. This is a collaboration space. But you see this open area here, and that open area looks down into another collaboration space. And that's the Judith and Jonathan Liebman collaboration space, which is down here. So lots of very nice, well-lit, cool collaboration spaces there. So I'm hoping to convince you that this building is going to be a very nice one. An interior look at the Alumni Center on the 3rd floor. I pointed it out on the outside. Lots of windows and a nice view. We're going to move the Benyon Library to a room in the building, and that's how it looks right now. It'll also serve as the Quaid Lounge. The William and Elaine F. Hall classroom, this is on the ground floor. Of course, no seats or other furniture in there yet, but you get an idea of these kind of large tiered classrooms. And this one actually can accommodate 136 students. And like all of our existing classrooms, I think you'll see that we will be outfitted with the top IT technology, teaching technology, and remote learning technology here. So this will be very good classrooms. Typical faculty office on the left. It's already starting to get furnished, and an example of that graduate student space. So we have lots of different kinds of space. And finally, this is the corridor on the ground floor. Again, we're looking east. And I just wanted to show you this because I think it's going to be a very nice lit space when it's finished. Along here, we will have 3 commissioned artworks on display. One will be along the wall here, a very nice glass piece. We'll have another piece down here, and then one behind the perspective. We'll also have a new display of Concrete Canoe, because after all, we are the developers of Concrete Canoe. So we've selected 2 iconic canoes, which will hang here along with a display to kind of pay tribute to our history there. I also wanted to point out this kind of interesting wave wall. Again, a lot of this pays tribute to water and water resources. And here you see this kind of interesting kind of gypsum board wave patterns that run all along the top of the hallway. So very unique features. And by the way, this is the Snow Ink Water Teaching Lab, which I showed earlier. Okay, now to the bridge. So as I mentioned, this is more than just a bridge. And this bridge was made possible by a generous donation from the Kavita and Lalit Bahl family. So you'll see here, this is just a drawing of the bridge, and maybe it doesn't look so impressive, but when you see an artist rendering, you'll see that it's much more than a bridge. It's a connection, it's a collaboration space, and so on. And it's also an instrumented bridge, which will provide data and opportunities for student learning beyond anything we've ever had. And so I'll kind of focus on that aspect now. As you'll see, this is just an overview of the kind of instrumentation that we are currently installing into the bridge right now. So we have, as I said, a permanent weather station on the top. I'll give a little more detail there. We will have an array of vibration sensors all throughout the bridge. They'll be hidden, so students won't see the sensors and the cables themselves. So we've designed it so that they're not seen. But they'll provide lots of interesting data about the behavior of this bridge. We also have expansion sensors, which monitor the expansion joints on either end near the abutments of the bridge. And then all this data has to be collected and stored and so on. So we have an acquisition and storage hub design. So the idea is to provide a living laboratory for civil engineering students and their classes in years to come. By monitoring temperature changes and movements and so on, this can feed directly into structural systems class. The vibration sensor array can feed in directly to dynamics class and so on. And it gives the opportunity of the students to actually be involved in the data collection and so on. And so here I want to acknowledge all of the people who helped. It was not just me. So Professor Bill Spencer and Professor Jim Lefebvre were key in helping get this going and designing and thinking about it. And two graduate students, Nate Levine, who is a PhD student of Bill Spencer, and Sang-Min Lee, PhD student who studies under me, were really instrumental in helping us get this started. All right, so let's take a look at what we're going to do here. So I'm going to maybe go over some details of some of these sensors really briefly, just to tell you what they're doing. So first of all, we have a weather station, and weather stations don't look like the old propellers and windmills of the past. They're modern and sleek and small and nondescript, but they provide a tremendous amount of data and information. So here you get wind information, directions, speeds, barometric pressure, temperature, RH, and all of that stuff in this little thing. This runs through the roof, and a cable runs to the data collection hub. So we're continuously collecting these data. So for instance, while continuously collecting data, we may have a huge wind event or a storm event. Well, we can monitor that, and we can monitor the response of the structure, which can be useful for students, and maybe it can be useful for researchers. All right, so these data will be continuously collected. Now we're also monitoring like simple expansion of this entire bridge. Bridges move a lot when they heat up and shrink when they get cool, and there are other influences like relative humidity. So we'll be monitoring all that. And this is a relatively simple case. There are expansion joints on the north and south end of the bridge near the abutments. And we will have this kind of simple extension gauge, Tokyo Measurements Instruments Lab extension gauge, just monitoring displacements again continuously. Now this will be hidden. It'll be out of view of the students, as will the cables. Now I'll spend a little bit more time on the vibration monitor. So in order to monitor how things move over time, that is how they vibrate, we need to measure motion at a lot of different positions and preferably in different directions. And so the way that we'll try to, and that way we can build back the complete story of how this bridge, the structure, is moving under external load conditions like storm events, or by our own generated events. And I'll explain a little bit more about that. So we designed a dense array of sensors, and these sensors are called accelerometers, and basically they're motion sensors. They're monitoring the acceleration or the motion of a surface that they're mounted to. And we have 28 of them. 20 of the floor of the accelerometers are mounted on the floor level of the bridge on either side along beam lines. And you see that there are red ones and blue ones. And the red ones measure vertical motion, and the blue ones measure horizontal motion running east and west. So we're monitoring the motion going this way, and then we're monitoring the motion going out of the plane. Also on the roof level of the bridge, we've mounted 8 accelerometers. All of those again are horizontal, going east and west this way. And this is designed to be able to capture all the meaningful modes of movement of this very unique structure, right? And again, this data will be collected. We can collect it continuously, or we can collect it as we so desire. And all of these cables from all the sensors will kind of be run to a storage, a data collection and storage hub, which is housed in a separate small room on the other side of the bridge. So just a little bit of information for those of you who are interested in dynamics. The sensors, the accelerometers we are using are very high sensitivity, flat, low frequency accelerometer made by PCB. So this can measure very accurately and consistently over a range of up to 200 hertz of vibration. And that's pretty wide range for structural measurements. It can measure up to plus or minus peak, half a G of acceleration. And so that's reasonable. And the sensitivity is quite high. So we should be able to measure very small movements. And that's important because, as you may have seen or guessed from the drawing, this is a very stout structure. We don't expect it to be swaying a lot. So the question is, what are the modes and can we measure them meaningfully with this system, right? And so we've designed the system to hopefully do that, to have the right sensors, have them in the right place, and have them in the right direction so that we're able to capture all of that. So now, this is a drawing. This is the bridge heading north, heading into a collaboration area. And all of the cables, these are all cable sensors, all of the cables are going to run in conduit through the roof level, out of view, above ceiling, into this room here. And this is a kind of a storage space for this associated sensing classroom. And so all of the stuff, all of our DAQ will be housed there. And so we have multi-channel DAQs, that's digital acquisition systems where the signals come in, they have to be converted into a form that the computer can read and store. And for those of you who know DAQ, you see that this is a good system. It's a 24-bit, so it has very high precision. Its sampling rate is 51 kilohertz, kilosamples per second. It's well above what we need. So we're going to have very accurate capture of these motions. And it also has features that are useful in avoiding noise, such as anti-aliasing filters. So we have these different kinds of acquisition units. They plug into this rack-mounted system. Of course, there's also a computer that drives the whole thing and other kinds of power supply and so on. And that'll all be housed in one cabinet right here. So how did we design the system? How do we understand where to place them and what we need, and if we can even measure anything? Well, we had to come up with a model. And I want to give credit to Nate Levine again, that's Professor Spencer's student, and Professor Spencer for coming up with this numerical model to simulate the bridge. And here you see kind of the simple model, this simplified version of the model that we use that's simulating kind of the mechanical response of the bridge. And we used an approach called finite element simulation. So that's a computer simulation that can simulate stresses and strains and movements and accelerations totally in the computer. So here you see the details of the model. For those of you who are interested in structures and structural modeling can see, but you see that we simplified it. You know, we have a kind of a simplified roof model. And we simplified things to kind of capture the motions that we think are going to be meaningful for the motion of this structure. Okay? And then I believe Nate is online and Bill Spencer's online. So afterwards, if you have questions about this, they'd be glad to answer, I'm sure. So let's look at what this model says we have. So what we have here are the outputs of the model. And what I'll show you are cartoons. They're animations, which are exaggerated motions, but motions that the bridge we expect will have and at the frequency that is the repetition rate that we expect them to have. So the first one is, you see the first vertical mode, and I call it first because it has the lowest frequency. So we can expect that this particular bridge can move like this. And I think some of you who had a dynamics class before or understand dynamics can see that, oh, this is kind of an interesting feature, is that our model predicts that our lowest fundamental mode, vertical mode, has 2 nodes in it, right? It has 2 nodes. If we look at the next mode, the next overtone, we see that it only has 1 mode. That's kind of unusual. So it'll be interesting to see, this is what the model says. So model says that we have these fundamental movements at low frequencies, 3 and 4 hertz. Will the real bridge move like that? Well, that'll be interesting to see, and it'll be a great study for the students to evaluate and compare. We can also expect some torsional modes. Torsional modes are twisting modes. And so this is the fundamental torsional mode. Again, it has 2 nodes in it, so that's a feature of this structure. And then the next overtone only has 1 node at higher. So again, can we excite these nodes? So I want you to remember this motion, especially this motion, and then the fundamental motions that you saw vertically before. Remember what they look like and remember those frequency values, right? We can expect some lateral motion. So here you see kind of the fundamental lateral bending mode. That only has 1 node. That kind of looks like more what we expect. And then the next overtone, here you see has 2 nodes. So we can expect those kind of motions. That's bending at the floor level. But we can also expect, because of kind of the differential stiffness of this structure from top to bottom, we can expect a different kind of motion at the top, right? So we have a lateral mode at the roof level, right? So based on our models, based on the actual design of the bridge, this is what we hope that we are able to capture due to external excitations such as wind and temperature and so on. And also internal excitations, us jumping up and down, and see if we can excite those and how the structure really behaves and compare it to the model. So how would students do that? Well, a very simple test that can be surprisingly effective in causing structural vibrations is called the heel drop test. And as it sounds, you have a person who stands on their toes and drops onto their heels, and it provides a dynamic load, a pretty significant dynamic load. And that dynamic load is shown here over time of the heel drop that's put into the structure, right? And so here you see a 9 repeated heel drop. So it's putting in a significant amount of load, and this person is pretty consistent. Well, here we'll show some examples. This is from our model because we wanted to see, can we even do heel drop tests or other kind of internal dynamic tests that are safe to do by the students to excite these modes and measure them. So from our model, what I'll show here is an output from this particular accelerometer, which is mounted on the floor. And then we'll simulate 2 typical human heel drops at the center of the bridge going vertically. So the force is going up and down out of the screen. And then one that's also going up and down, but it's a little bit offset from center. All right. So I want you to go back and remember those motions, right? So when we have a heel drop in the center, perhaps we can expect some of those vertical movements. Maybe not a torsional and a lateral bending, but we can expect some vertical movements. And here, maybe we can expect, because we're a little bit off center, some vertical and some torsional movements. But again, probably not any lateral bending modes because we're not exciting it in that way. So here you see the output. So this is, what this is an output of the response of that accelerometer that I indicated to 2 different heel drops. One in the center, and then one offset, right? And so what these peaks represent are these different modes at different frequencies. So the x-axis is frequency, and you remember the frequency is this measure of how often this thing is vibrating. It's measured in hertz. And you'll see here that based on our calculations and based on the system we have, that if we do a heel drop in the center, we can excite the first and second vertical modes, and in fact, perhaps even other vertical modes, and then other modes we haven't computed yet. So we're getting data, at least out of the simulation, right? And when we go to the offset response, we can see that we also get the vertical mode, but we also get the torsional mode here. So we are able to excite that. So that's exciting news for us, because that means that honestly, we had some concern that this very stout, stiff bridge is going to be very difficult for students to kind of excite these modes and use conventional methods to to get these modes of vibration and measure them. But our model suggests like, nope, we're fine. Our system is good. We're measuring the right things. We're using the right tools to measure them. And we will be able to get meaningful data, not only from the external excitations like wind events or storm events, but also from students doing heel drops and people walking across the bridge. So another thing that I think is a very nice feature of this is the bridge is not only the bridge, but the abutments of the bridge, underneath the bridge. The abutment is, of course, the end where the loads are transmitted from the bridge. And another faculty member, Dr. Tuche Basser, developed instrumented foundation under the bridge too. And I'll talk a little bit about that. I'm much less familiar with this work, but I think Professor Basser is online, so she'll be able to answer. But the idea is that the best kind of illustration is here, that under the bridge abutment, we have 4 deep foundations. So they're drilled shafts, kind of piers. So they're acting like piles to transmit the load into the till. And we have 4 of them, and they're instrumented, right? And so you can see the hole being drilled, the cage being put in, and I guess concrete being placed. And Dr. Basser wanted to acknowledge that this was done in collaboration with the FNS, our Facilities and Service of the university itself, and the Student Sustainability Committee on campus, because these are instrumented geo-energy piles, right? So there's a lot of interest in this kind of technology from a sustainability point of view. The university is very interested in this technology, right? So just a snapshot, we're looking here, this is Newmark. Some of you will recognize that. So we're looking south, and just different kinds of sensors that are mounted directly into the cages, which are placed into the holes in the ground, right? So we have thermistor strings, we have strain gauges, right, to measure strains and so on, but temperature is also important. And we have a fiber optic cable running all the way through. It also measures data such as temperature and so on. So sophisticated technology in these piles, but they are drawn out, they're data logged, and they'll be used, first of all, to monitor the long-term performance of these energy piles. How are they doing? Will they continue to be efficient over time? And plus, it provides data for classes that deal with this. So for instance, our advanced graduate level deep foundations class, 585, can make use of the data that come from this. So I'm at the end of my talk, and I wanted to say, what's next? I think that I can say that this, what we call phase 2, the new civil environmental engineering building, and especially the Kavita and Lalit Bahl Smart Bridge, really build on great improvements that we have done to our infrastructure. And that great improvement is the Jeffrey Yeh Center, which many of you may not know, but it was built, I guess, finished over 10 years ago. And it provided, it was built on the northeast corner of Newmark, and it provided great new teaching space for us, which we were very short on in Newmark. Newmark was a great lab, but it didn't have much teaching space. But here we provide this great collaboration and teaching space. And, we, at the time, I think through some wise decisions from leadership, and in particular, I'll point out Benito Marinas, Bob Dodds, and Jeffrey Raisler decided we are going to invest in the best lecture capture technology and distance learning technology that we can, right? And we did. All of the classrooms here and all the classrooms in the new building will be outfitted with this. This was well before COVID. We were ahead of the game. And so when COVID came and we had to move to online, we were uniquely prepared. And I think we still, I tell people that the University of Illinois and Champaign-Urbana is the best place to live through COVID, because I think we are handling it better than almost anywhere else in this country, right? We have an excellent facility that are able to develop these tests that get us rapidly tested. and so on. And we were ready for distance learning. So I was really, really proud of what we were able to do. And to this day, civil engineering is ahead of everyone else in terms of providing online and distance learning because we invested in that technology earlier. And yeah, most of our classes have a face-to-face component now. Other departments can't say that. And moving into the fall, when the university really wants everybody to move back, for us, it'll be a seamless transition. We will be ready because we invested in the future with the generous donations of our incredible alumni, and we're not stopping here. We have further plans to continue modernization to stay on top of the civil engineering game in this nation and in the world. But we need your help, we need your insight, we need your support. So thanks very much, everyone. I hope you enjoyed this kind of view of our new facility and the Lalit and Kavita Bahl Smart Bridge and Civil Environmental Engineering Building. I'd be happy to take any questions that you may have.
Hey, John, there's a couple of questions in the chat box.
Sure. Sure, I can try and I'll try to handle them if it's that okay with you. I'll read them.
Yeah, that's fine. Yep.
Well, first of all, to our distinguished alumni, Chuck Haas. And Chuck, I want to say, first of all, big congratulations to you. Chuck was elected to the National Academy of Engineering. And, I'm very happy for you. I'm very happy for Drexel, and I'm happy for Illinois. I mean, you are in Illinois, and so we're very happy about that. Chuck says, John, is the street going to be open to traffic, and will your bridge sensors be able to use the traffic as a forcing function for the structural response? Well, it's a great question. The road under the bridge will not be open to real car traffic. It's a kind of a pedestrian zone. Of course, there will be some vehicles that will have to come in from once in a while. So we will not be able to use this kind of ambient vibration from the traffic. However, we do have plans in that area with our transportation group to kind of study vehicular traffic, and in particular autonomous vehicular traffic in this area. So there are plans for that, but great question. All right, next question, John Conroy. John, can you explain a little bit more about the Geo-energy piles and foundations? I, again, am not very familiar with that, but I welcome Professor Bosser to, if she is online, to talk about those.
Sure, I'm here.
Great.
I'm happy to talk a little bit more about the Energy Foundation project. So just a little background. So because Professor Popovics mentioned that he's not super familiar with the project, it's because it all happened really fast. And I came in very late in the design of the building. And then I said, why not convert these foundations that we were going to have anyways to become energy foundations to contribute to the sustainability of campus. So there are 8 drill shafts that are supporting the building. And initially we thought of converting all those foundations to become energy foundations to provide some portion of the heating and cooling of the building. So then we decided to go with 4 because of the cost and concerns and issues. But so what is a foundation, a drill shaft, and what is an energy foundation? So let me give you a little bit background what they are and the difference. So you're all familiar with the foundations and drill shafts, one particular foundation, but these ones, we include high density polyethylene tubing to circulate a fluid through the piles to exchange heat between the surrounding soil and with those pipes of the fluid that are circulating within the pipes. So those, we inject usually cold water, and then it circulates through, it gets warm. And then when it comes back up, it goes to a heat pump system that are installed in the building that is helping distributing the heat and cold into our rooms. So we initially thought that we were going to cover everything, but we decided with 4. But then because of the contribution of facilities and services, and they said, we said, okay, why not heat and cool geotechnical engineering laboratories? So we have two geotechnical engineering laboratories in the new building. And then we develop a bypass system. So the building gets its heating and cooling loads from a central system. But so we implemented another system where we can cancel that central system and we can only run our function our piles, energy foundations to provide heating and cooling. So, and we instrumented it with all the necessary instrumentation that required to monitor the performance. And since this is the first energy foundation installation on campus, we are going to use this as a baseline. We are going to validate our numerical models to actually elaborate it for the whole campus for the future construction efforts as well.
All right, thanks very much, Tuche.
Sure.
I think the next question I saw was from noted alum Amanda Bordelin. Hello, Amanda. Are you all marking the floor where the sensors are so the students know where to activate it? You know, that is a great point. No, we didn't mark the floor. The sensors are hidden away away for the architectural reasons to make this space kind of inviting and this nice collaboration space and so on. But we did not mark. The plan is that we will have on display a screen running all the time that will kind of show active data. So this is more just for passersby to, not for real rigorous data collection, but say, oh, look, this is what the bridge is doing today. This is the temperature, this is the expansion and so on. So I think that's a good idea that maybe we indicate on that screen where those sensors are. So I think that's a great question.
And so you can take your class there too.
That's right. That's right. That's the idea, right?
Yeah.
Okay, next question. Again, it looks like Tuche, it could be for you. So how does the diameter of the 4 energy foundations compare to that of the others?
So there are 8 of 6 foundations. They have a diameter of 4 feet. And then the 2, So 6 of them having a diameter of 3 feet and 2 of them having 4 feet. So John, if you can go back to the slide where I'm showing where the, So you see these like 2 at the top, they're 3 feet, and the others like at the very back having 3 feet diameter. And then the lower ones that are circled with red, so they have 4 feet. So we do have multiple loops installed, multiple U loops installed in these 4 foundations to be able to actually investigate the effect of having more contact with the piles as well. So there's a very significant research component here and also a functional component as well. I hope I answered that question. And I see another question, I'll just continue. What depth do the piles sit at? So they're at 60 feet below the grade. So they can be maybe 65 feet because there was an issue during the drilling. So they encountered a very loose sand layer. So then we were, scared that it was going to create a problem. So we drilled a little bit deeper than that.
Great, thank you. Next question from Wissam. How are you measuring the weight of the pedestrian traffic going into the bridge? I am assuming that this information would be important to tie the structural behavior to the acting load. Right, so you're right, that would be information that's useful, but we did not put in any kind of weigh in motion or anything like this. So we don't have any system that can measure the loads. But what we can do is initiate kind of standard or known loads. So like, for instance, heel drop. Now, what is the level of the heel drop, in terms of the actual loading? We won't know unless we measure that separately. But we can have those, and we can also have rolling loads of known weight. But unfortunately, we couldn't work in this weigh in motion kind of feature.
Do you have any other questions out there? All right. Well, if not, then I'd like to start by thanking you, John, and the rest of the team for this. Is a great presentation. I'd also like to thank everyone for attending tonight. It was a great turnout. I'd also like to thank all the donors for their generosity, and especially I'd like to thank and mention Kavita and Lalit Bahl, who are they're on the call with us tonight. So again, thank you for your generosity as well. Just checking the chat box one more time to see if there's any last minute questions. And I think that is it. So again, thank you everyone for joining us tonight, and look forward to seeing you again, hopefully soon on campus. So again, take care and have a good night.